All right, hello everyone. My name is Mark Vakarchuk. I'm from the junior team of detecting changes in algae growth using multispectral imaging here at JMU Engineering. And the teammates are Jorge, Charles, Caitlin, and Christian. Advisors, Dr. Enriquez. So, what is eutrophication? Eutrophication is a very complicated state, but it's can be summed up as over nutrition overloading in water. This is generally caused by fertilizer runoff, which can lead to algae blooms. Fertilizer is added to fields, golf courses, farmer fields, especially to growth in the to assist in the growth of vegetation. But when that happens to end up in water, it also assists the growth of vegetation, and this generally happens in the bloom of algae. In the U.S., there's approximately $2.2 billion worth of damages from algae or eutrophication related events. This can be broken up as 50% of this is from the loss of revenue of boating, fishing, camping, parks, and general recreational activities. Though another large part of it is restoration and cleanup of the algae in water. These values of 2.2 billion is on the lower side of things, with some estimates going up as high as $80 billion in damages in the U.S. alone. So, as we can see, this is a large scale problem. Our project spent the fall semester, a good chunk of the fall semester, looking for people who are interested in this and who are able to help and be stakeholders in this project. We came across Ken Benson. He is the Potomac Regional State Park Manager, and he oversees a large body of water. And so they obviously deal with a lot of algae there. You can see him right here on the right side. The image on the right that we can see is algae actually flowing down a river. It is a very visually unappealing thing, but more so than that, it can be poisonous at times. And so they use satellite imagery right now just to get a bird's eye view of the algae. But this is one of the biggest complaints that he had is that satellite imagery of algae, or in general, satellite imagery is very low resolution compared to what a drone could provide. So he's very interested in the prospect of using drones to increase the resolution and therefore make better decisions. We also work with Smith Mountain Lake. They have a large water surface also, and they actually are very interested in doing water testing. They've been doing extensive water testing at their lake for 47 years now. And this water testing stations that they have around the lake leaves a lot of empty gaps of knowledge, you could say, between the testing points. And so a drone that could fly over the whole body of water would be able to fill in these gaps where there's not where it's not being tested right now. Also, we're interested in the idea of potentially working with Heritage Oaks here in JMU, Harrisonburg, close to JMU. They're local to us, they're close, and so that would be a very convenient place to fly tests locally here instead of having to drive out to the Potomac National Parks or to Smith Mountain Lake. Another stakeholder that we end up working with is the FAA, just because of drones, and they oversee the regulations and rules of who can fly where, under what conditions, and so on. Also, I'd like to take this moment here to talk about the picture on the right. This actually explains, like, lets us look into a very important aspect of it. Cameras can only capture what they see. Algae is very surface level problem, but it can also go below the surface, and it's not able to see what is below the surface, and so that adds a challenge to this capstone. This capstone can be broken up into two major components: the capturing and the analyzing portion. First, I'll talk about the capturing. Drones is a very common technology, and many people are aware of the basics of it, how it can fly and go anywhere, and it's the versatility of it compared to a satellite imagery, which passes every so often. You cannot control when a satellite passes day, night. You cannot control the cloud coverage, and you can't choose when it will fly over. So by having a drone, it gives a very large flexibility. It also increases the resolution that can be captured. The Centennial satellite, which is a satellite by the European Space Association, has a resolution of roughly 10 to 60 meters per pixel. When you're looking at oceans or coral reefs or large bodies of water, that's perfectly fine. But when you're looking at lakes or rivers or ponds that can be in total 100 meters across, this does not give the resolution needed. This camera that we see at the bottom left, the Alum camera, it has a resolution of 5.2 centimeters per pixel, significantly better than the meters ranges of the Centennial. And this 5.2 centimeter per pixel data is taken from a 400 feet height. This 400-foot height is set by the FAA. It is the limit for drones to fly in the US. We will never be flying drones at this altitude even, so our resolution will be more precise than this. Another advantage of multispectral images, which most people are not as familiar with, The fact that it's multispectral, it kind of hints at the fact that it's multispectral. It does beyond the human vision, it does beyond visible light. It can go into the near infrared, into thermal imaging also, which has a thermal camera on board. So the multispectral cameras have a very narrow bandwidth that they see, so they can see blue, green, red, red edge, and near infrared. In general, these bandwidths range anywhere from 20 to 40 nanometers at a very specific wavelength. So you're able to capture the data and see exactly what is going on at these specific wavelengths. From here, there's formulas that you can calculate the vegetation reflection, water reflection, and you can very accurately tell what's going on and what's on the surface level without a person having to look at it. The second important aspect of this project is the analysis. Because of just the way that this semester turned out, we were planning to use this spring semester to capture and fly the drone and capture data of bodies of water here around Harrisonburg. But because we're not able to be on campus, we're not able to do that. The senior team that is doing a similar project looking at vineyards, they have provided some data that we are actually running and starting the analyzing process with and starting to stitch the images together, analyze, run NDVI that we can see here in the bottom left. But we've not been able to capture any data of bodies of water on our own. This is why we see a vineyard here instead of a pond. But this still allows us to capture and start planning out the program and writing the scripts for stitching the images, for analyzing the algae, for analyzing the water presence, and so on. This analyzing portion consists of two main parts. We have chose to use ArcGIS because of Ken Benson and their government agencies use ArcGIS often for other things, including mapping and just keeping track of all the places within their state park. And so by using ArcGIS will fit right into their workflow. We have an add-in portion which will be the user interface for the person to use, as well as an analyzing portion which is made with a combination of tool sets from built into ArcGIS and Python scripts to do special functionality that we need that cannot be accessed through the tool sets. Currently, we are in a fairly early stages just because we haven't been able to capture our own data and fly. And given how seasonal and cyclical algae is, this will have to be we'll have to wait to capture extensive data as much as possible in the early weeks of the fall semester, just so we can have something to analyze throughout the winter of the following year. If there's any questions, I'll be happy to answer now.